We are now beginning to work on exam 4. Inverse functions is the first part of this. Before we can do inverse functions, we need to talk a little bit simply about functions. Identify one-to-one functions. Now, what I'm talking about here, when I use the phrase one-to-one, that sounds kind of scary, but in reality, it's not. It just has some certain requirements, extra requirements beyond what is a normal function. Okay? Now, in this particular case, I want to use an analogy. An analogy of a square and a rectangle. Okay? Now, squares and rectangles are kind of alike. In fact, a square is a specialized rectangle. One-on-one is nothing more than being a specialized function. Okay? A rectangle, all four corners got to be 90. On a rectangle, opposite sides got to be the same. That's basically the requirements. What are the requirements of a square? All four corners got to be rectangles. Opposite sides have to be parallel, but also all four sides must be congruent, the same. So square has that one more little requirement over a rectangle. Well, one-to-one is just a simple one requirement on functions compared to any function or what we call a relation. Okay? A relation is any equation where you can have an x and a y, and depending on what you put x in there, you get some y value. And we've used function notation before. I don't want you to spend time copying that. If you got this set of values, now what this set of values represents is we had some function, some y equals mx plus b, that we put in x values, and we got these y values. Or that function could be y equals x squared plus 3x plus 2. Or that function could be y equals x cubed plus 27x squared, and so you get the point. Okay? Some function, some equation, putting in x values produce these y values, is what all we're saying here. Now, in this case, determine if the relation, so far we just know that an equation produced it, so it's a relation. We want to see if it's a function, and it has that special requirement. Now, in this case, this has its unique, this x value has its unique y location for the point. Okay? This unique x value has its own unique y value. This one has its unique, and that one has its unique. This one we would consider not a function for one reason. Look at this. This x value has that y value. This different x value has that same y value. Now, is that okay or is that not okay? Well, let's look at this. If we had a graph of just a standard parabola, f of x or y equals x squared. Those 2 points would be in that. Here's positive 2 and up 1. Here's negative 2 and up 1. That's what that's saying. Okay? Now, so we would have that point and this point represented. This is a function. Okay? Now, let's keep going in this and see what it says. We have the same y with different functions. That means this one is not one-to-one when we talk about one-to-one values. Okay? Now, look at these two Venn diagrams. This maps to that. This maps to that. This one maps to that. All of these have unique y values for each x value. Okay? So yes, it is one-to-one. Now, it is a one-to-one function if no horizontal line intersects the graph in more than one place. Now, before, let's go back to my parabola. We had done the vertical line test to determine is a function or no. Correct? So this parabola is a function. But based on this rule, it is not a one-to-one function. With the definition of one-to-one, that each x has to have its unique y. A different y. Okay, no two x's can have the same y value, is another way to put that. Okay, and we call that the horizontal line test in this case. Now, the inverse, that brings us to the inverse of a function. Whoops, let me put that back up. Interchanging the first and second coordinates of each ordered pair produces the inverse. What that's saying is you just switch the x and y values. X becomes y, y becomes x. Okay? And that's going to have some particular effects on graphs and anything else. And we'll talk about that as we go on in this chapter. Now, look at this equation. That thing is a parabola, right? With a modifier on it. If we factored that thing, it would have been x times x minus 2. So we know what that thing's going to look like even. It would have been x minus 2 would be right here at positive 2, and x itself would be 0. And so that, and here's my y-intercept in this case. This is a parabola that does something like that. Okay, in very general terms. I could figure out the y-intercept, but the vertex, but it's not that important right now for this problem. This, in turn, is the inverse. Notice we replace the y with x, and we replace the x's with y. Okay? Now, that's going to give us a flipped picture. But the two are going to be reflected across a 45-degree angle. So I know the picture I drew was slightly wrong. Now, look at this one. Do I have all unique x and y values? X and y pairs? Yes, I do. Okay, so here are the points up here in blue. To make this more obvious, I'm going to play dot-to-dot puzzle. Okay, this is going to make it a little more obvious. Notice here, the X's and Y values interchange. What used to be -2 for X is now -2 for Y. What used to be +3 for Y is +3 for X. What used to be 2 for X is now 4 for X and 2 for Y. They just flip the values in all cases. Believe it or not, on the final, you will probably have a problem as simple as this one. Okay, they're gonna say, they're gonna give you, they may just draw the line and not even give you the points and say graph the inverse. Well, if they just gave you this line without giving you the points, you'd have to figure out the points, graph the points, and draw the new line, the inverse line. Okay, and there's one question on your final and on my test that are probably no more complicated than this one. All right. With that, we're going to stop right here because it's time.